Okay, let's get started. I want to talk about parallel algorithms. That is not the first talk about parallel algorithms. I hope I'd give a different spin. Most of the others actually talked about the standardization or how to implement that stuff. I don't want to talk about how these things are implemented. I primarily come from a user perspective, and I try to use these things based on the standard specification. So I want to talk a little bit about how these things are used, what the requirements there are, what the experience so far is, and things like that. So, yeah, a little bit of copyright. We all know lots of concurrency around. Unfortunately, actually also in different ways. So far, C++ has basically standardized concurrency on different cores on the same system. Any other concurrency using things like SIMD or GPU or FPGAs is relatively left uncovered. However, the idea of the parallel algorithms is partly to say implementations have a hook where they could plug in a hint that things should be executed maybe on a GPU or on some other device. So that is something which hopefully these things go one step towards unleashing. That said, C++ is unfortunately entirely sequential. If you specify something, there's no concurrency in there. We basically have to expose the concurrency to the compiler so the compiler has a chance to do something. That goes in multiple ways. The first thing is if you actually just provide some code to the compiler often has a hard time to detect whether he can possibly make things parallel because he doesn't see all the implementation. He may not be able to analyze whether these things are actually wouldn't introduce data races at race tree. It may also not be able to actually detect whether it's worth its while to actually try to do these things in parallel. So we basically need to help the compiler out, at least for the time being. Maybe some of these things go away in the future when we have a better idea how to do things, similar to inlining, where compilers nowadays have a much better idea how inlining worked. In the beginning, we needed to specify that. It goes more and more away. But basically, for now, we need to express the ability of asynchronicity. And the parallel algorithms are in that space. So here's a simple example. Everybody has written loops which do a lot of work. And this thing can be made nicely in parallel if the function is, well, first of all, typically doesn't have a side effect. If it has side effect, it probably has data races, so it can have side effects to some extent, but you need to synchronize on these possibly. Then accesses to the iterators shouldn't introduce data races. And there's another requirement over here, and that is either size is reasonably large or function takes a lot of time. If neither of these are given, if the size is small or the function is actually relatively fast, almost certainly trying to do these things in parallel doesn't really pay off. And we may be able to tell the compiler to do that. There are already ways to do that. For example, OpenMP. I've never really used OpenMP, but there's a way to use OpenMP. There's a subtle change over here. This loop uses not equals, which implies it would work for any kind of iterator, whereas this guy uses less than, indicating that it's actually a random access iterator. And OpenMP, as far as I know, only works with random access iterators, whereas the parallel algorithms target also non-random access iterators. So you can use them with bidirectional iterators or forward iterators. Input iterators are currently not required to be supported, but they can work on possibly other iterators. Whether that is a good idea to use is a separate question, because the system still needs to iterate over these guys. It cannot jump and basically batch things up. The thing in OpenMP, well, it doesn't make a promise that things do execute in parallel, and it doesn't make any promises about things possibly being able to nest. In particular, the nesting bit is if you is unspecified. That is if you have an algorithm or loop which does work, and you actually inside that, you may be able to parallelize more. That doesn't cover that. So there are a number of constraints, and also it doesn't really fit the language. Kind of slapping these pragmas on top of it is not a really nice approach. We could do something like that. That is rather hacky code. It works, right? We all know, all right, there are threads, just kick off a thread for everything. This uses a batch size. The idea over here is doing every function in just one individual call is probably not a good idea. You probably want to batch these things up and basically process whatever, have 1,000 calls or 8,000 calls or how many calls you have in each run. Stick these threads into loop, then we eventually at the bottom we need to essentially synchronize to get rid of these things. If we didn't have the for loop where we join all these guys, we would terminate when destroying that stuff. That looks horrible. I don't want to write any of that stuff because normally my loops are not as structured as that. There's normally a little bit more inside the function and it becomes messy if I start putting anything in there. And it's also not necessarily efficient. If you try to use it on different system, it actually executes not faster than sequential, sometimes even slower, even if you have a lot of work to do, which is basically down to some systems actually really create a thread and destroy a thread every time. So it gets slow, where some other systems actually kind of have a pool of operating system threads and actually just schedule them. So this is something we could do, but we probably don't want to do. Of course, we all get told we can use async. Well, that's not a big difference, right? We can use async. We would do get. I also don't want to do that. Something which is more in the direction of what I actually would want to do is what thread building blocks do. I don't know whether anybody used thread building blocks. And that's basically a parallel for, where you stick in a function and you specify a range. One of the things the parallel for does is it basically calls a function object which you stick in with the range itself. The range basically is adapting to some grain size, where the algorithm somehow figures out how big should the grain size be, so that it can, on the one hand, schedule these things to avoid imbalance things, while not creating too much overhead to make things inefficient. For some algorithms, that is actually, well, there are some algorithms like that, and it makes it somewhat easier to use than the thread stuff, but there's still quite a bit of stuff around that. And it would actually be nice if the inner function block would be done inside an algorithm. So what I would like to write is more something along those lines, which basically says transform, and I say, okay, I stick in what is called an execution policy, and otherwise nothing changed. So I had my transform, which I had before, begin, end, destination, and function, and I just execute these things. And that is the direction which the C++ 17 standard took for the parallel algorithms. There are still problems with these guys. This is one of the things is these algorithms basically return. So basically there's a similar synchronization on all of these threads. So basically if that guy has finished, it returns on the same thread instead of possibly being continuing elsewhere. So there's a synchronization similar to the OpenMP stuff at the end. But it's a reasonable direction which is expected to be extended upon, built upon. And actually, if you went to Hartmut's talk, he already talked about these things, saying, all right, maybe transform shouldn't really basically synchronize and return the result, but rather return a future, so you basically can schedule the future elsewhere and keep your system busy. This is currently not part of the C++ standard, but that is an expected direction where I expect things would go. So there's some expectations once we start passing in an execution policy to say what our algorithm actually is constrained to. And in particular, these assumptions are that the functions somehow, whatever that exactly is, do not introduce any data races. And the other part is that the arguments typically can be copied so that you can actually stick them onto different function objects, send off to different threads. So hopefully everybody's using algorithms a lot. If people use algorithms a lot, the change from the status quo to just getting things faster can be very easy, because all we have is that, and we move it and just stick in parallel a couple of execution policies, and everything hopefully just works. Using, sorry, what?
The destination doesn't exist, but it's giving dynamic construct.
Oh, okay, okay. So the question is, what happens if these things actually do not write to a destination range like in a vector, but rather it's writing in an empty vector and it's basically back inserter which pushes to the back? The answer to that is the algorithm has to work that somehow out. I'm relatively sure that transform will not perform particularly well in parallel if you actually build a range. It can do something reasonably smart, possibly, if it understands what back inserter is, to basically say, all right, I know how that works. If I basically batch these things up, I know how many batches will be produced, and basically coerce the vector and back inserter into not really doing back insertion. And basically go and say, all right, we basically trick the back inserter into kind of, well, pre-allocating all the memory and then passing in the buffers. The algorithms are relatively flexible, but is to some extent, or to a large extent, the responsibility of the user to use them in a reasonable way. Otherwise, the parallel algorithm still cannot do anything. So that is the easy approach. Obviously, it's probably not so easy. I don't know about your place, but where I work, hardly anybody ever uses algorithms. So just slopping anything in doesn't quite work, because typically people actually do write the loops, which is rather annoying, and over here is the real reason why we could do differently. The other thing is just sprinkling execution policies over your code also probably won't work, because you actually need to understand whether loops execute a reasonable amount of work or not. It does not pay off, and I hope to show that a little bit later, to try to parallelize small, fast executing loops. Executing heavy loops, which actually do a lot of work, certainly does pay off, but if they're too small, it won't. And the other thing is, you need to be careful that the execution of the function, for example, doesn't introduce data races. If it introduces data races, all bets are off. That's basically undefined behavior, and the compiler, the system cannot necessarily tell you at of time whether that would actually work, or whether there are actually issues. So just sprinkling things over is not the thing. Which gets me to the concurrency model. In general, the standard is specified to say, right, we work on basically a broad range of hardware. All of these algorithms, all of the functionality should be available on all of that hardware. Some of that hardware actually doesn't have any concurrency at all. And actually probably would make things just slower trying to emulate concurrency on systems like that. As a result, there's no promise that a parallel execution, even if you say, right, a pass on an execution policy which says run in parallel, does anything in parallel. It is giving the algorithm the opportunity to execute in parallel, but it doesn't make a guarantee that it will execute in parallel. Now you can go, oh, well, that's really bad, so implementers do a bad job. Well, this is what the marketplace is for. It's quality of implementation, and you hopefully choose a decent implementation and just go tell the others to improve, or you won't buy their free product. Oh, hang on. But there's a full expectation that there will be decent implementations. The other thing is, by passing whatever execution policy you pass in, there will be execution policy specific constraints on what the operations, or requirements on what the operations have to do. I will go a little bit more into detail when talking about the specific execution policies. To actually talk about the constraints, it's important to understand what an element access function is. There's a new term in that with the introduction of the parallel algorithms, and basically an element access function is any function which is passed in as parameter and is specified by the algorithm to be used, or is specified by standard to be part of being used in the algorithm for some purpose. So typical element access functions are the operation on iterators being passed in, or function calls, or any operation on function objects being passed in. There may sometimes be other element access functions like swap, where the algorithm explicitly says this uses swap, and the constraints for the corresponding execution policy apply to all of the element access functions. What is important over here is the iterator operations often are specified, well, most of the algorithms are specified in relatively relaxed iterators. For example, they take forward iterators. However, the element access functions are not just the forward iterator operations, but they are the operations of the iterator category you pass in. So if you pass in a random access iterator, all of the random access functions qualify as element access functions. Likewise, all the operational and function objects. What does not qualify as element access function is anything which the algorithm may want to use and may try to sniff out whether maybe that such a function exists. We can do that quite easily with metaprogramming. However, algorithms, basically the parallel algorithms, are not allowed to sniff out whether you have some other operations which it may consider to be useful, because there's no guarantee that that function actually would be data race free. The guarantees, the promises you are making about your arguments only apply to the functions which are specified or the iterators passed in according to their respective category. Okay, so that's a little bit tricky. And then based on that, we get a number of execution policies. Currently, the standard defines 3, sequential or sequenced parallel and parallel unsequenced. There is also an execution policy type trait, which is intended for detection. It does not work and is unspecified what happens if you to define your own execution policy and try to pass that into the standard library algorithms. The reason is each one of these execution policies actually does something entirely different. This is basically just a way to give the same interface to essentially entirely different functions with a relatively easy hook how to change these functions without having them in different namespace or different name. So the execution policies are specified by the implementation, and you cannot really hook your own in. You can create your own algorithms and pass in whatever execution policy like thing you want to do over there, including the standard library ones, but that algorithm is your business. The standard library algorithms only work with the ones which are specified, and whatever the implementation, in which case you become dependent on the implementation, whatever the implementation offers to use. The expectation is that implementations will prototype additional execution policies, for example, to execute on an FPGA or maybe execute on a remote machine or whatever crazy idea these people have and they think they can do. These are the ones which the standard currently specifies, and future standards hopefully extend on that. The execution policies are objects. The future, one of the expected changes in the future is that the execution policy gets replaced by something like an executor interface, where you can pass in an executor and the implementation will be in terms of that executor. So there's a future expectation that you can change how the parallel algorithms would execute in parallel, but that is not there yet, partly because the concurrency group has not finalized an executor design. In fact, there's, as far as I can tell from the outside, still a lot of contention on different ideas what executors should do and how they should look like. So these are the 3 execution policies, and we'll quickly go over the constraints. There's execution seek, which is basically for sequential execution. That's a little bit weird. Why would I have an execution policy for sequential execution? One of the answers is it's for debugging. So if you actually want to have something which behaves roughly the same with respect to all the other constraints as the parallel execution policies, you can use seek. Another reason may be that you have fallback and you have some generic way to determine, oh, this is how big the range is, and so you basically decide at compile time which execution policy this particular part of the algorithm should use, and sometimes it should be sequential, sometimes it should be parallel. This is what you can use. The execution policy still imposes, although it is basically just the same as a sequential algorithm, some changes in what the algorithm does. In particular, any exception which escapes from any of the what do they call them? The element access functions is basically resulting in terminate. There's no way in parallel algorithms to really report exceptions. There may be multiple exceptions thrown from different threads, and once things get into something like more GPA or SIMD execution, there's no way to deal with exceptions anyway. So basically exceptions is, at least for now, left open, and it results in terminate. There's no required for input iterator support. You can clearly implement something like a sequential transform on input and output iterators. However, there's no real way how you could actually deal with input iterators which yield a move-only type and make that parallel. There are some things which are basically very unclear how that can be done. Implementations, if they figure out how to do that, are free to support input iterators, but there's no requirement for them. So basically, if you want to have portable code, you can use the parallel algorithms at best with forward iterators. To some extent, I think most of these discussions are relatively academic because most of the time you want to execute on random access iterators. And finally, there are a number of algorithms which have slightly changed constraints or slightly changed return types. In particular, for each, this normal for each returns a function object. In a parallel context, you actually want to have for each just executing as fast as it can. If you do things in parallel, which of the function objects do you want to return, you would need to combine them. There's an algorithm which combines the result to some extent, which is called reduce, rather than for each, and you would use that. So there's some changes in the interfaces and the requirements on the arguments, and I will try to point them out. So these are the constraints for sequential. That's not particularly interesting, but the common interface changes are common to all of the three standard execution policies. What is way more interesting, and certainly is in the space which currently works for some implementations, and something which I'm interested in is par. This is basically executing things in parallel. This is basically thread parallelism, where the constraint is none of the element access functions can introduce a data race. If you copy any of these guys or execute any of these things, there shall be no data race. In theory, you can use locks inside any of these functions if you have to. I need to synchronize and I take a lock. It is probably a bad idea because you want to execute things in parallel, and locks basically, well, you can call them slowdowns or something instead of locks as more descriptive. Every time you acquire a lock, you basically synchronize things, and everybody who wants that lock stops. But you can. The main thing in comparison to the next one, there's no interleaved execution. So it's basically within a thread, just a normal execution of your element access functions. And then there's something which is called par ANSI. The idea over here is now the element access functions can execute in parallel. You may have actually multiple additions happening at the same time on multiple elements, functions being called in theory on concurrently or in parallel on the same thread. So that is targeting things like SIMD parallelism or GPU parallelism rather than thread parallelism. Obviously, over here, in addition to not having any data races, you cannot have any lock because the thread would deadlock with itself, possibly. Two separate threads executing on this, well, two executions on the same thread could just both acquire the lock and you would have a deadlock. So these are the execution policies and their requirements. Moving on quickly to what algorithms are supported. Yes? What is the default execution policy? Well, there's no default execution policy. It's actually the first argument you pass into an algorithm. So if you do not pass in anything, you get the existing sequential algorithms and none of that stuff applies. If you pass in a execution policy, you know which execution policy you pass in. Does that make sense? Okay, so the next question is what algorithms are supported for the parallelism. There's a huge number of operations supported, but not all of the algorithms from the standard library are supported. Roughly speaking, all the things which make any sense to be in parallel are so basically are not just sublinear, like anything which is logarithmic or just a constant operation is probably not viable for or not reasonable to do things in parallel. Some algorithms seem to be unsupported, but are really supported under a different name. And then there are some algorithms which are relatively rarely used and fairly complicated, and I'm not sure whether you can make them in parallel. They're not there, and then there are some oddballs which are not supported, for which I have not found a good reason why they're not there. but I will go over those in detail. So you're not expected to read that. This is just qualitatively everything which is green is supported, everything which is red is unsupported. So it's actually the majority of things are supported. That's good. So the reason the things which are not supported is, for example, these guys. They're all of one algorithm. So it's just, they're just one element operations. Doesn't make any sense to support those. The next thing are logarithmic operations. Even if you have a tremendous range, you actually do not get enough operations to make it worthwhile to do these things in parallel. There's basically all the log n algorithms, like finding something or inserting into a heap. Then we get a number of heap algorithms. These are both linear algorithms or n log n algorithms. I think they're both linear. But the thing over here is the heap operations mess entirely with the entire range of the heap. Trying to do that in parallel, I don't see how you would do that. It kind of is probably also something I cannot see a use case for having these. Similarly, the permutations is basically how do you permutate these things in parallel. It's relatively unclear, and although some people have claimed they have used these, I've never seen any of these algorithms used in production. I've seen them used in test drivers. Then there are some algorithms which are not supported because they overlap. That is copy backward and move backward. The copy and move operations are actually not allowed to overlap in the parallel stuff because it doesn't make sense to overlap them. It's okay if you're sequentially overlapping them because you can, assuming you move through the right direction, you copy before you reach the thing as a destination. So that's okay, but in parallel, it doesn't make any sense. So copy backward and move backward don't make any sense. Then we have accumulate, which actually accumulate and partial sum. They are taken out because they're renamed. They're basically called reduce. And then we get these three oddballs for which I have no reason why they're not there. I think sample in particular could be done. Shuffle probably accesses everything. Maybe that's not a good idea, and iota is kind of a generational thing. I believe these things are not entirely there, in particular shuffle and iota, because they just came too late in the standard of C++17 and or 14 even, and were not didn't make it into the paper. This is my personal guess. Okay, with that said, these are supported algorithms. Now, not all of these supported algorithms are necessarily super efficient. So let's go the other way around and see how I would imagine these things can be implemented and which ones are expected to be fast. So the obvious massive parallelism, the embarrassing parallel stuff, that would be basically a variation of map. This is a whole host of algorithms which actually can just execute in parallel. They have no real interaction with each other. Although, as was pointed out, something like transform or copy, if the destination does not yet exist, there is actually an interaction between these guys, and they may need to fall back on a different algorithm. But if you execute them on random accessed ranges which do exist, these should all be mapped and should be really fairly efficient, assuming you have enough operations in them. So the idea of map is rather simple. In a sequential thing, you just execute one at a time. In parallel, you just execute things in parallel and just get a nice speed up. With par_unsec, you can basically execute multiple operations in parallel. This just display almost certainly these things won't be entirely in parallel, but rather slightly offset. But roughly speaking, there should be a nice speed up if that is actually attainable. There are some additional constraints, as I mentioned. The for each functions do not return a function object, as they do in the sequential stuff. Copy and move are not allowed to overlap. I didn't find a constraint that copy n is not allowed to overlap. So you can copy n elements. I don't think that is intentional. I think that is more like an error. And then some of these algorithms may do something more complicated, maybe something like a reduce, maybe something like a gather-scatter thing, if you execute them on non-random access iterators. So, but this set of algorithms would be expected to be really fast. And there's a whole host of algorithms which can essentially be mapped to something like reduce. Reduce, essentially what it does is it can also execute things on parallel sequence, but after the sequences are executed, you basically need to combine the result to achieve the final result. There's a whole bunch of these things which are find operations. I don't know whether find operation can be done in general nicer in a way. Probably there are other parallel algorithms which can deal with that, but reduce can certainly deal with that as well. And one of the things which is kind of obvious from the idea of doing that, if you use one of the find operations, you probably only want to do that if you're looking for the needle in the haystack. If you expect to find something really soon, you don't want to have the parallel find. It will find one of the guys, and if you try to kick that off in parallel, it will at least search in a number of ranges and possibly omit later ranges, but it's almost certainly less efficient than actually doing things in sequentially. So if you really search for, in a huge range, the one element, if it exists, that may be reasonable. Otherwise, you're probably better off doing a sequential stuff. So reduce, similar. Sequential does it sequential. In parallel, basically combines, there's a little bit of combined steps at the end. And in parallel, you basically execute on within the thread some combinations of the different ranges and then some combined step. So that's, again, expected to be really fast. There's some changes. Accumulate becomes reduce. I mentioned that. The operations in there need to be associative. Otherwise, you get a wrong result because there's no promise that the operations are done in the same order at all. They can be in a different order. And that's a little bit of a bummer, right? We basically, the expectation when you say think accumulate, probably in most cases, we accumulate things maybe in a matrix multiplication. All of these things are doubles. Double addition is clearly not associative. Now, the algorithm requires that these things are associative. I don't think it says that it's entirely disallowed. And basically, the net effect of basically using non-associative algorithms may just be that you get a wrong wrong result. On the other hand, if you do double additions, you already know that you get a wrong result. You just get a different wrong result. So there's a little bit of a trade-off. You don't get necessarily the result you expect. You get some other result that should still be fine. However, formally, these things should be associative. And I'm already mentioned that find may be tricky and stuff. So then another bunch of algorithms, exclusive scan and inclusive scan. These are basically the same as the partial sum stuff. So the idea of partial sum is you basically compute not just like in the accumulate or reduce the sum of all the elements and just have the final result, but you also compute the sum of all the intermediate results. So you basically get the entire range. Inclusive scan, exclusive scan, as well as partial sum seem to be algorithms you don't use very often. Interestingly, they are rather useful to implement other parallel algorithms. So there's actually inside the parallel algorithms area a good use of these things. In particular, if you basically try to do a filter, if you filter things in different ranges, you basically get a new range with different number of elements, and then you can do the partial sum to figure out where things really need to go. The algorithm is a little bit more complicated. It's still a decent parallel algorithms, and you can do nice tricks to do that basically well, if you have enough processes in logarithmic time instead of linear time. But yeah, it's a little bit more special case. There are two. There's inclusive scan and exclusive scan, and they're slightly annoying. So the idea is the inclusive scan is basically, or the difference between the inclusive scan and the exclusive scan is what is the first element, which value is used for the first element. For the exclusive scan, the first element is actually the initial value you pass into the algorithm. For the inclusive scan, it is the initial value, is the first element of the sequence plus or combined with the initial value. Depending on what you try to do, one or the other is actually what you really want. as a result, it makes actually sense to expose both of these algorithms. You can, in theory, implement one in terms of the others, but this is neither direction really is good. You lose a little bit of efficiency in both directions. To make that a little bit more annoying, similar to these algorithms actually, unfortunately, have a slightly different parameter order. And that is similar to partial sum. These guys take a range, and then they have an operation and an initial value. For the inclusive scan, typically the initial value is defaulted, and you're mostly interested in the operation. For the exclusive scan, the initial value is the first element. You're probably very interested in passing that, and instead often you have addition as the operation. So they actually, the last parameters are just reversed, the initial value and the operation, and they're correspondingly defaulted. So this, what is to be said about these guys? Then there's a bunch of entirely new algorithms: transform exclusive scan, transform inclusive scan, and transform reduce. Essentially, the idea over here is you want to do as much work on elements as you can at a time. You don't want to basically run over the same sequence multiple times and apply multiple operations. These guys basically fuse the operations into one. They basically fuse the transformation in addition to whatever other thing they do. I could imagine that in the future with the ranger stuff, we get a lot more of that. They basically would produce a range which basically fuses many operations, and you basically have a pipeline of operations, and it's more like an expression template thing. You try to build up a big operation on the individual elements, and then you execute these individually. For now, we got these guys. And then we got a number of gather algorithms, or scatter, which basically combine determine where things go and then distribute them. So basically, you could imagine that over here, these things make sense if any of these operations, like the condition for copy if is relatively expensive, then you could run the copy ifs in parallel, then find out where things go, and then distribute these things, so to reduce things. These are relatively complicated algorithms. I haven't experimented with those, but I think they can be executed in parallel and should have a benefit. And then there are a number of remaining algorithms which I left as specialized. The intention over here is all of the other guys, basically you have a few core algorithms and you basically map that into these algorithms, and then there's a number of algorithms left over which you probably have to implement, or the implementer has to implement individually. But that, despite the relatively big starting set, there are not that many parallel algorithms which in the end really have to be implemented. Most of these things are just mapping on other algorithms. Okay, which leads me to availability. When I proposed that thing originally, the idea was, all right, cool, I whip out the compiler and run things, and things should work. Turns out none of the compilers currently, none of the standard libraries actually chips with the parallel algorithms. According to P024R1, this is a paper which proposed adoption of the parallel TS, the parallel algorithms from parallel TS. There are multiple implementations of all of these algorithms. I checked all the implementations which were listed. At the point where I first checked, all of them were partial. None of them actually implemented any of the interesting ANSI stuff. As far as I know, there's still nobody who implements the ANSI stuff, because most of this time, the only way I can imagine how these are implemented actually does require compiler support, and I haven't seen any compiler actually getting around to implementing the ANSI stuff. In some stuff where you basically pass in a function object and the compiler somehow figures out to create a new function object which can be executed on multiple elements in parallel or something like that. There's an expectation that these things would happen, and some of the players in that field seem to be working on that, but I haven't seen any of that. So the proposal was a little bit optimistic in my opinion, but nonetheless we got the algorithms. So the current implementation status is all of the if you look at that paper, you find, I think, 6 or 7 implementation listed. All of them are partial. None of them support parANSI. Most of the implementations don't even try to fall back to a sequential implementation to say, right, we have at least all of the things. You have the signatures and it compiles. It just runs in sequentially, which I would have hoped to, at the very least, to say, right, yeah, you try to do these things and we haven't covered that as quality of implementation. The only implementation which by now seems to be reasonably complete, at least all algorithms I've tried, is HPX. HPX is not living in the correct standard namespace. It's basically an implementation. It's an open source library. You can download, compile. It provides all the interfaces with correct semantics. And it seems to be complete on x86 or the 64-bit version thereof on Linux. I've not managed to get it to work on macOS, and it outright says it cannot work on ARMs. So there are implementations around, but they are incomplete. If you try to use HPX, it kind of tries to set up its own environment, and you basically need to do a little bit of fuffing about, like main needs to delegate after initialization or with initialization to a different kind of HPX main. And the algorithms are living in HPX parallel instead of the normal standard namespace. Okay, with that, is it actually worth considering all that stuff? Yes?
How do you control how many threads
Okay, so the question over there is, how do you configure how many threads are to be used? The answer to that is, at the moment, there's no customization ability to specify how many threads you can use. In the future, the expectation is, as I said, that we basically hook these algorithms up with the executors, and we would control the number of threads or the available parallelization resource via the executor. The current standard entirely says, it doesn't speak about that, it just says, right, here are the algorithms, here are the execution policies, this is what you get. Okay? So, I tried these things on a couple of machines. One of the machines has plenty of cores. It's an Xeon Phi, 64 cores, 4 times hyper-threaded, lots of memory. So that is kind of a surrogate for something which is server-like. Then the middle guy is a kind of reasonable sized desktop machine. Actually, it's kind of a Mac with 4 cores, 2 times hyper-threaded, plenty of memory. And then the last one is an architecture which always is too slow. That's just a Raspberry Pi, but it has 4 cores, right? Why not try it over there? Let's see whether these things work. And the first obvious test I wanted to do is, let's try a map. So basically the moral equivalent of this loop, just using different parallel implementations. Given the state of the available implementations, I cooked up my own, plus used some of these things as wrappers around TBB or OpenMP. So with all of these things, this is not what the standard necessarily does. It uses a standard interface or something very close to the standard interface, just living in a different namespace. And the standard library implementation should outperform all of these guys, hopefully. But this is what I could test with. So basically, all of these guys will have basically a blue line, which is the benchmark. This is the sequential implementation of, in this case, stood for. There is a thread implementation and an async implementation, which is roughly speaking the code which I showed you earlier. The code earlier was for transform, this just for each, but roughly doing the same. There is a power implementation around a homegrown thread pool and a TBB implementation, which is basically just doing the same thing, trying to wrap TBB. So, and the results look something like that on a Xeon Phi. And the red line down there is actually the TBB implementation. The green and yellow line, async and stood thread, is basically using threads. And then my implementation trying to do a thread pool is in the middle. The cool thing over here is saying, all right, a good implementation easily outperforms the thread stuff. In fact, if I try to not run that with GCC, but rather with Intel compiler on that machine, or with Clang and their respective standard libraries, the results for the green and yellow line would be even worse. They actually seem to create a new thread every time, and they actually do not outperform. They're actually slower than the sequential implementation. But over here, you can see there's actually quite a nice benefit already, although there's not a lot of concurrency available over here. We don't really do, most of the stuff is just traveling around memory. So on a desktop machine, none of these things work. It's just basically, if you look at the sizes, they're already fairly large, and getting anything bigger, there's not enough memory to actually make any sense. It would basically start going to disk, making things yet slower. So these guys on these on a desktop machine don't help. Interestingly, on a Raspberry Pi, doing things in parallel does speed up a little bit. At least you get kind of double the speed. In the end, where these things go up, I think it probably hits the memory limit already. These ranges are substantially smaller, but it doesn't have much memory. Now, doing something a little bit more interesting, this is nice computation using very little of data. If you look at what that is, it's kind of doing these Mandelbrot computations. In the past, when I grew up, I did compute a screen full of dots with a bad printer, and it took hours. This program now with huge amount of things takes still just seconds, but it's basically a nice big workload for each thing. It's still the same for each thingy, it's still the same implementations, and the results look actually a lot more promising. There's a huge speed up. You don't get the line on the bottom looks as if, oh, it takes 0 time. It is not 256 times faster, but it's about, roughly speaking, in the best case, something like 100 times faster. So it actually benefits from the hyperthreading. Since it doesn't access any memory, it's kind of executing nice and fast. I have not been able to try to actually use SIMD operations to do the same thing. I would expect that that would actually get things yet faster. So if you have nice workload, there's a potential of actually improving performance dramatically. The same is true for the desktop machine. If you actually do not make it not memory bound, you basically get all 4 cores busy, and you execute 4 times as fast, which is nice. On the Raspberry Pi, it's a little bit more confused. There's no consistent result, but it's still faster, and it keeps the machine busy. Another interesting result may be sort, if you need to sort huge ranges. Unfortunately, I didn't manage to get any other parallel sorting algorithm to work, like the HPX stuff does work, but only on the Linux machine. So, but there's a nice speed up of these guys. Again, this is using 64 cores, but it only gets about, I think in the end, around 16 times faster. All right. No, sorry, this is not quite 16 times. This seems to be 8 times-ish. But which is still a nice speed up if you actually need to sort huge arrays. It does benefit from that. Likewise on the desktop machine and on the Raspberry. Again, a little bit more confused, but you get a speed up. And then finally, reduce, where basically you need to compute first and then you need to combine these things. Again, relatively simple. It just reduces, just computes the sum over a range. I get a number of implementations there, which I try to use, which is accumulate the benchmark, power using homegrown thread pool, the OpenMP implementation, which is basically a standard interface on top, around a loop labeled with OMP, and the thread building block version. And they also, even if you just do a relatively simple operation, get a nice speed up. So I think these things are kind of all, so on the desktop machine, not as much, but still it gets faster, and on the Raspberry Pi it's a little bit confused. So all of these things do make sense. They do get faster, but you need to actually give nice workloads and relatively large ranges. One of the things which I didn't show is most of these ranges start at already relatively large sizes. If you make them actually just a bit smaller, the algorithms tend to be way slower. So the my naive implementation is sometimes a few thousand times slower. Sure, at that range, the algorithm doesn't take long at all, but it's still slower. The OpenMP and TBB versions tended to be also quite substantially slower. So not just a bit slower, but massively slower. So I would hope that a proper standard implementation actually covers this area more nicely to basically decide that, oh, this range is too small. I will do a sequential version rather than trying to schedule things. Okay, so as general guidance, I have tried some of these things with the HPX implementation with forward bidirectional iterators, and it's a lot worse. So all of these things do not get as much speed up at all. So in general, try to use random access iterators if you want to use these things, and your operation need to be worse parallelizing. So basically, you need to have a sequence with large ranges or really expensive operations. There are a number of future directions. I already mentioned some of those. That is, we do expect that the algorithms will be augmented to take an executor as a first parameter, where the executor is actually user-specifiable customization point, where you basically say, how do you execute things where? Hartmut already mentioned that in HPX, there's also a version which implements future support. So instead of basically waiting on the thread, you get back a future by basically passing another parameter or different parameters execution policy to say, all right, I want a future back, and you then use it. You basically don't wait on that thread. You just basically combine these things and wait somewhere else, which basically allows for much nicer balancing utilization of the cores. I would expect that there's also eventually some control over chunking, so that you basically can decide what grain size should be used. But none of these things do exist, and there is work on the executors, but I haven't seen any proposal in any of the other spaces. One of the things which I'm personally interested in is saying I would like to use an interesting execution policy which says constant. A lot of people ask for const expr algorithms. Now that we have a hook, maybe if you stick in constant and make these const expressions, that could be a nice way to avoid having to do kind of the general purpose algorithms be const expr and basically having to avoid certain algorithms, certain optimizations. Because if you look at something like sort, that may actually want to invoke mem copy on integers rather than trying to swap these guys. But a const expression version would not allow that. So there's a potential idea to actually kind of abuse the execution policy. And yeah. So in my opinion, using SCL algorithms is good. You can then sprinkle the execution policies. And the parallel algorithms work best on large and random access stuff. And with that, I think we have some time for questions. Yes?
You mentioned that with the sequential execution policy that the algorithms could call terminate essentially.
Yes.
Is that also true for the other execution policies?
Okay, so the question is I mentioned that just on the sequential thing that it may call terminate. And there were a number of other constraints like the interface changes. All of these changes I mentioned on the sequential stuff to get them out of the way. They apply to all of the standard library execution policies. There's a potential in the future that we may have execution policies which say, oh, if you throw an exception, it won't terminate, but does something else. But at the moment, the element access functions are constrained to not throw exceptions, otherwise they will terminate.
When do you think the entire feature will be available in standard compiler?
The question is when will all the features be available with standard compiler, standard libraries? The answer to that is I actually have no idea. I could imagine that some implementations decide to use actually HPX and delegate to HPX, which would at least give the parallel stuff and potentially some level of ANSI where they can figure out some SIMD stuff. Any compiler support, I have no idea. The compiler vendors tend to be a little bit, well, I cannot look at what they work on in general, Maybe I could. Maybe we can ask Richard, but I don't think Richard is working on that area, and he's shaking violently his head, so he isn't. So I hope that would emerge soon. Part of the reason to do the presentation is that people ask their compiler vendors or drum up interest. Because there's one thing, if nobody is interested in that stuff, most vendors probably go, well, there's no user interest. We would implement it once there's user interest, but if there's no user interest, so it's a little bit of a chicken and egg problem. You guys have to be interested to get that stuff, to give incentive to the vendors to produce it. The vendors need to produce it so that you guys get interested.
Yeah, another exception question. Is there a specified set of guarantees I can give as a caller so that the algorithm would guarantee?
Okay, so the question is there a set of guarantees the caller can give to the algorithm so that the algorithm by itself doesn't decide to throw an exception? I think none of the standard library algorithms actually is currently specified to ever throw an exception. Any exceptions thrown would be kind of when having undefined behavior. There would be no guarantee of what happens in undefined behavior. So for example, if something accesses out of bounds stuff as part of a function being called. And otherwise, I think the standard actually would have to list if it throws an exceptions willingly. So I would expect that there's no exception being thrown. I would need to go through all the standard library algorithms to figure out what they exactly say, but I don't think they allow, the standard library algorithms are allowed to throw exceptions just because they feel like it. Okay, any other questions? Yes? The question is whether a corresponding feature is available in other languages. I'm sure that there are some languages which provide some parallel algorithms, but I'm not an expert on any of those. So I'm not aware of any mainstream language which provides a corresponding set of parallel algorithms. Okay? Is there no more questions? Then thank you very much.